Hello everyone, welcome back for another video. In the last video, we have seen how to use the functionality of writing to the pin B register to toggle the corresponding port B. And the assembly that was generated by the compiler Avr-gcc looks like this. Let's make it blink 4, and then to see the assembly I will use this program called object dump. This was the assembly. I said that there is some instruction that is not really useful for this particular program. I don't know why Avr-gcc put it, but in any case, we will try to write the program in assembly so that we have complete control of everything. This is actually the advantage of writing in assembly. You can basically do whatever you want. Also, I say that these two instruction is basically equivalent to pin B equals to 1 left shift 5. I say that we can use this instruction called SBI to just set the particular pin, which is the 5th pin of port B, which is this register. So let's also rewrite these two lines in just one line like this. So I have already written the assembly program. Here it is, blink5.asm. Let's open it here. It is basically the same thing as blink4.elf, except that I got rid of some other stuff that we don't need. So I put everything as it is. The first line I kept it, but for the second and third instruction I replaced it with the SBI instruction. It says set bit I to the register which is located at this address. The register located at this address is pin B. We can go back and see that here. Pin B is at address 03, and then set the 5th bit. So basically by writing it this way we saved 2 bytes, which is not a lot, but when you go down to 20 something bytes, every single byte matters. And then we have these 3 things. Everything here is basically responsible for the delay. I will see if I have time to explain this, but for now it is just this code is responsible for the delay. I also got rid of these 2 kind of useless lines instructions, at least in this program. I think Avr-gcc is putting it for optimization or whatever. We don't care for now. I just removed them, and instead of jumping, I used these labels to jump to the corresponding addresses. So let's compile it and see how many bytes we get for the program here. And since this is assembly, we will use a program called Avr-as, which stands for Avr assembler, I believe. And the program that we want to assemble, then we supply the .-o parameter to tell what will be the name of the output. So let's call it blink5.o, not elf. Let's call it object file. We will see what that means. And then let's also tell the microcontroller that we would like to generate code for this assembly. You know, different microcontrollers within the AVR might not have the same instruction set. So everything is done successfully. We see a file blink5.0 generated. This file is not like the others. It's not like this elf file. These elf files, they are executable files. When I mean executable, they specify the load address of the sections. Like this section should be loaded at this address in the memory and stuff like that. But the object file, they are called relocatable or something. They are not really executable. It doesn't tell where the sections in memory should go. This video is not about explaining the Linux executable and linkable file system, but there is some difference. And to know that whether this is executable or not, we can actually see. Let's object dump, disassemble it, and see the code. We can see that the branch instructions, they are not branching to anything. They are just branching to zeros, both of them, which means the addresses hasn't been known yet. Does that make sense to you? But if we disassemble the blink4.elf, we can see that we are jumping to something useful. Well, this was useless. It doesn't really matter. But this one is branching to some number, and this one is branching to some number. Not for the blink5.0, because it's not executable. And we can also use this program called readelf to kind of make it human readable. Let's say blink4.elf, and it will tell us that it is an executable file for Atmel Avr 8-bit microcontroller. Focus on this file, executable file. And then we will do the same thing for blink5.0. Where is it? Yeah. This case, it is relocatable. It's not executable, but relocatable. It is for Atmel Avr 8-bit and some other stuff. We can also see that there is no program headers in this program. But anyway, we have to convert it to loadable or to executable. And to do that, we will use linker, which Avr-gcc has. So Avr-gcc, the input file is blink5.0. The output file, we can call it blink5.elf. And I guess that's it. And if we use the readelf program, we can now see that hopefully it is executable. Yep. Now this is executable, and we can upload it to the microcontroller. But let's see the size first. I mean, I'm wondering how much it will be. 20 bytes? Are you kidding me? Let's see what the previous value was. It was 26. Now it is 20. Because we got rid of some, I think, 3 instructions. Let's disassemble it. Avr. My laptop is running out of battery. That's why it's lagging. Sorry, just 1 second. Okay, Avr object dump disassemble blink5.elf. And if we add another terminal here, not this one, let's split it. Let's get rid of this. I'm trying to compare it with the assembly generated by Blink4. And everything is the same except I used one instruction SBI to replace these two. The rest is the same. And I also got rid of this relative jump to nothing, to just the next instruction, and this no op. So 1, 2, 3, 4. I'm counting the bytes that we got rid of. 1, 2, 3, 4. And yeah, like 6 bytes total. Clear. 20 bytes for Blink 5. Let me upload it. I'll make Blink 5.bin first and then upload it. Yep, thank you, Avr-gcc says. And I can see the program is blinking every 1 second, it looks like. Sorry, I am not showing you in the video, but just trust me. In the next video, I will upload all the programs from Blink 1 to Blink 5 and see on the oscilloscope if it is actually generating the correct signal. That is, turn on for 1 second, turn off for another second, and do it forever. So we have seen various different ways to reduce the number of bytes required to blink the program. Hopefully you learned a lot of things, like how are the C statements translated to assembly, and when should we use the assembly. In some cases the compilers will not generate the code that we want, or the compilers will add some extra instructions that are not desirable for our particular purpose. In that case, we have to write them in assembly, just as we did today. And hopefully you also see that how hard it is to write in assembly, and we have to appreciate the compilers which are doing everything for us. So that's it for the video. Maybe in the next video I will explain how the delay is created. So far I just said this program is responsible to cause a 1 second delay, but I haven't really explained how it does it. Maybe in the next video I will do it, but for now this is it. I hope you like the series. Please support the channel by liking and subscribing and telling your friends. Thank you.